The topic of this lecture is confidence intervals. We start with a quick reminder. Population and sample. This is concepts I introduced to you during the last lecture. Population is all possible results, and it's characterized by some unknown mean, standard deviation, and other parameters. And sample is a set of n measurements with the mean, capital M, standard deviation, SD, and also other statistics. So we can find M, for example, the mean from the sample, but we should ask ourselves, how good is this M? How accurate is our prediction? We want to build a confidence interval, a certain range from M lower to M upper. This is the notation I'm going to use, L and U, where we can expect true mean with a certain confidence. We have done it to some extent during the last lecture. I introduced the standard error of the mean, and it expresses uncertainty of the mean. But this time we want to introduce a more strict measure, which is called a confidence interval. And something like a confidence interval can be calculated not only for the mean, but for any other parameter of the population, like median, standard deviation, correlation, proportion, etc. What is confidence? Let us consider a 95% confidence interval of the mean, which is very commonly used in biological sciences. And you can understand how it works in terms of repeated experiments. Imagine you do a very simple experiment. You have a sample of mice, let's say 5 or 10 mice, and you calculate the mean body weight of these mice. And this is the mean here, the dot represents the mean, and the gray arrow bar represents the confidence interval. At the moment, we don't know how to calculate it, but let's say for a second that we can calculate it. And then we repeat the same experiment with another sample of mice again and again and again. And this shows results of 100 repeated experiments. This is what you normally don't do in science, in your laboratory expertise. You only have one experiment. But the concept of the confidence interval is as follows. If you repeat your experiment multiple times and calculate a confidence interval for each result, then the true unknown mean, which is represented here by the red dashed line, the true unknown mean lies within this confidence interval 95% of the time, 95% of cases. The true mean will be within the calculated interval, or alternatively, in 5% of cases, 1 in 20, it will be outside the given confidence interval. And these cases outside are marked here by black arrow bars. That would be a false result. That would be where the true mean lies outside our predicted confidence interval. So in this case, if you set your confidence interval at 95%, then you have a 5% chance of producing an incorrect result. This is the meaning of the confidence interval. Confidence interval is not, I repeat, it is not the probability of finding the mean in this interval. The true mean is not a random variable, it's a fixed number. It doesn't have a probability distribution, so you can't find a probability of the mean somewhere. It is the other way around. It is the probability of you quoting a result consistent with the true mean. Now, why do you use 95%? Well, it comes back to Ronald Fisher, a statistician who wrote this book, Statistical Methods for Research Workers, and it is in 1925. And he thought that 95% confidence interval would be convenient, as it resulted in one false indication in 20 trials. It also corresponds to the statistical test probability p-value of 5%. I will explain the link between confidence intervals and statistical test p-values later. He just thought it was convenient, and he published tables of for a few probabilities. One of them included 5%, and this just stuck. Everybody started using 5%. This book was very influential. So that's why people tend to use 5% or 95% today. However, there is nothing special about 95% confidence interval or p-value of 5%. These are completely arbitrary numbers. Ronald Fisher, well, he was a statistician, probably one of the most influential statisticians of the 20th century. He developed many fundamental concepts in statistics that we use today. He was an evolutionary biologist. He went to Harrow, private school Harrow, and then to Cambridge. And the Harrow's schoolmaster once was asked to name 10 most brilliant boys who went through the school. He thought for a while and said, well, it will be difficult, but I would divide all those I had taught into two groups, one containing a single outstanding boy, Ronald Fisher, the other all the rest. So Ronald Fisher was outlier in those days. He was genius, but he was a bit of evil. He famously said that he didn't like administration people, and he famously or infamously said, an administrator, not the highest form of human life. Let's jump from Ronald Fisher to sampling distribution. I tried to explain it in the last lecture. I showed you the sampling distribution of the mean. The sampling distribution, you can build it in a Gedanken experiment or a thought experiment. In our case, it's a computer simulation. We consider an unknown population and draw a lot of samples of size n from this population. And from each sample, we can calculate an estimator. So if you calculate the mean, after many, many repeated experiments, we can build the distribution of the mean. But you can do it for anything, for the median, standard deviation, interquartile range, or any other statistic you can extract from data. All of these are called sampling distributions. This is sampling distribution of the mean. This is sampling distribution of the median, and so on. And if you remember, the width or standard deviation of this distribution is the standard error. So this would be standard error of the mean. Standard error of the interquartile range would be a bit different. And as you can see, this distribution is not symmetric. Now let's focus on the mean. This is the sampling distribution of the mean shown in this figure. And now the idea of a 95% confidence interval is as follows. This entire curve, all data here, contains all possible samples that can be drawn from the population. If we focus on the central 95% of the samples, and if we want it to be symmetric, we can simply cut out or reject 2.5% on each side, then that would be an interval containing central 95% of all samples. And this is what we want to find. This is actually the confidence interval of the mean. Instead of doing the simulation, what we can do, we can convert this to a known probability distribution, which is analytically known, and do some more calculations. We don't know this. We don't know the width of this distribution because we don't know sigma of the population. We can do the following trick. This is a very simple mathematical trick. Instead of the mean and standard error, we can calculate t. And t is mean minus population mean divided by the standard error. This is a purely mathematical trick. We can't find this number for our sample because we don't know mu, which is the true population mean. We use it only to do some transformations. But we can follow our Gedanken experiment, and the same way we build the distribution of the mean, the sampling distribution of the mean, we can create sampling distribution of t. For each sample, we can calculate this, at least in theory, and see how t is distributed. And it is shown in this figure. On the left, there is a sampling distribution of the mean. On the right, there is a sampling distribution of this value, t. And now, the important thing about this is that this distribution is known, and this is what has been shown in the beginning of 20th century by Fisher and a few other scientists, that this follows an analytically known t distribution. This is one of the probability distributions which I haven't mentioned in my first lecture, but there it is. It's called a student's t distribution with n minus 1 degrees of freedom. It's a simple distribution because it has only one parameter, number of degrees of freedom. And as you can see here, when the number of degrees of freedom is low, it starts with 1. It's much narrower than the normal distribution, and it's got tails at low and high values. When you have a lot of these degrees of freedom, when your sample is large, it looks like a normal distribution. And again, we come back to the central limit theorem. Essentially, in statistics, if you have sample which is large enough, almost everything becomes normal. It's a don't quote me, it's a simplification. But for a small sample, we have these wings here, which are higher than in normal distribution, which also means if we cut here and calculate some tail probabilities, they will be quite different from the normal distribution. This T distribution was developed by William Gossett, who was a brewer working for Guinness Brewery in Dublin, and he was also a statistician. And because he worked for Guinness, it was a private company, and they prohibited employees from publishing any papers. So he did some statistical discoveries, but he didn't want to, announce himself. So he published this as student. That was his alias. And he worked with Fisher. He developed T statistics in its current form. He worked lots of experimental data. You could probably call him a progenitor bioinformatician, one of the first bioinformaticians. This is the original paper published in 1908, the probable error of a mean. And this on the right, you can see a theoretical student's T distribution, which is analytical, which means we can do calculations here. We can calculate probabilities. We can cut off some regions and find confidence intervals. So with this statistic, which is very, very just a simple conversion of our original data, we can find this distribution, and now we can reject top and bottom 2.5%, and we can calculate the critical value. It's called critical value TC, and this critical value corresponds to 95% inside. You can use R function QT to calculate. This is fairly straightforward to do. And now our confidence interval corresponds to this interval from minus TC to plus TC. This can be done mathematically. All we need to know for this is the sample size, because the student's T distribution has only one parameter, which is degrees of freedom. And once we have found this TC, which is a bit of an abstract number, we can use our original transformation and find mu from this. So from this equation, you can find mu is m plus t times standard error. And you can plug in our confidence interval from minus TC to plus TC and find the corresponding lower and upper interval on the mean. Or you can write it like this, that the mu, our best estimate for the population mean is our sample mean plus minus confidence interval, where confidence interval is a standard error multiplied by this critical value. And this is the big picture, okay? This is what I try to explain. This is sort of an intuition behind it. This is not how you do it in real life, but this is the intuition. So you have sampling distribution of the mean where you are interested in finding a confidence interval, but we can't do it here because we don't know mu, we don't know sigma. We do a transformation to a known analytical distribution where we can cut off exactly the probability we want and find a critical T. We plug it into this equation, and finally we find the lower and upper limit of the mean, which in this figure is somewhere between 16 and 24. And you can do it mathematically, and you can find confidence interval for your particular sample. All you need to know is sample mean, standard error, and sample size. Have a look at this example. We have 5 mice. We've measured body weight, and here are these numbers. And from then we can find what I told you, mean, standard deviation, and standard error. Now, we use a T distribution to find a critical T. I will show you in a moment how to do this in R. This is a known distribution. So for a given number of degrees of freedom, which is sample size minus 1, so for 4 degrees of freedom, we can find critical T that cuts off 95% in the middle It turns out that this critical T is 2.776. And then we find the lower and upper confidence limits. Finally, we can write down our best estimate for the population mean is 23 plus minus 6 grams. You might be tempted to write it like this because these are exact numbers. The point is that most of these figures are not significant. And in one of the next lectures, I will explain to you how to quote number and its error. This is actually wrong. There are things here, these numbers are not significant. This is numerical noise. This is completely meaningless. So don't do this. I will tell you how to do this properly. And this is how we do this in R. So we first define a vector of our 5 numbers. These are 5 values of body weight of a mouse. The length is n. There is a function called length. The mean is capital M, and there is a function in R called mean. So you can quickly calculate length, mean, and also standard error, which is a standard deviation divided by square root of n. Then we can find a critical T corresponding to the number of degrees of freedom. And this is a reminder, I tried to explain this to you in the first lecture, how you can use functions in R to calculate things in probability distributions. If you remember P, so PT or P norm for normal distribution, for T distribution is PT, is this probability, cumulative probability from minus infinity to a given value TC, our critical TC. And QT is the other way around. It gives you the critical value for this probability P. And what is P here? Well, we want 95% here, but P is from infinity to this point. So it's 95% plus 2.5%. So our P is 0.975. That's why we need to find a T value corresponding to 0.975 and 4 degrees of freedom, which is n-1, the size of the sample -1. And this is the T, critical T value, which we found. And now we multiply it by the standard error and add and subtract from the mean. And this is which gives us lower and upper confidence limit on the mean. However, you can make it even simpler. You can use a t-test function, which is for a statistical test, but it also returns confidence intervals. So this is a one sample t-test. This is your sample. You put it in t-test, and the t-test result gives you lots of numbers, but among them, there is also a confidence interval, 95% confidence interval of the mean. And if you could compare it with the previous slide, these are exactly the same numbers we did calculating it step by step. What's the difference between confidence interval and standard error? Again, in my hand-wavy sort of a simulated intuitive explanation, they both come from sampling distribution of the mean. And this is the same distribution, sampling distribution of the mean on the left and on the right. Confidence interval is this interval that contains 95% of the samples. Standard error is the standard deviation or width of this distribution, and it's related to the standard deviation of the population with this simple formula, is divided by the square root of n. Now, this is a simple picture showing you a sample of 8 numbers, and I calculated the mean, standard deviation, standard error, and confidence interval. And this is a 95% confidence interval. The first thing, you can see that confidence interval is larger than the standard error. So we can ask the question, first, how many standard errors are in the confidence interval? It looks like about 2, but is it 2? And the second question, well, confidence interval is built for a given probability, 95%. If you reduce this probability to 80, 70, 60%, the confidence interval will be smaller and smaller. So you could find, in theory, you could find a probability that corresponds to the standard error. This will tell us something about the meaning of the standard error in terms of probability. And I did all the calculations. First of all, it depends on the sample size. And on top, you have the number of standard error, the 95% confidence interval. And I told you it looked like it was around 2 or so. And if your sample size is large enough, let's say more than 10, 20, 30, then it approximates this number 1.96, the magic number. This is the value that in normal distribution cuts off exactly 95% of probability. It's about 2. So that's what I told you, that for large samples, confidence interval, 95% confidence interval, it's about 2 standard errors. However, this is not true for small samples. In particular, if you have a very, very small sample of just 2, this number is about 12 or more than 12. So there are 12 over 12 standard errors in a confidence interval. This is bad, and I'll show you in a second why. The lower plot shows this the other way around, the confidence of a standard error. So what probability can we assign to a standard error? And again, for large samples where all distributions are almost normal, this is about 68%. And again, if you remember from Gaussian distribution, from normal distribution, the plus minus 1 sigma, plus minus 1 standard deviation in a normal distribution cuts off about 68%. This is the result. But again, for very small samples, especially sample size of 2, confidence of a standard error is very low. It's only about 50%. That tells you that you can't do experiments with very few replicates, 2, 3. It's not good. I told you before that you need replicates. Now I'm going to tell you, you need more replicates, more than you think. This is the difference between 8 and 100 replicates. Standard deviation, standard error, and confidence interval, and the same for n over 100. And as you can see, confidence interval is again about twice the size of standard error. But of course, it's much smaller here when your sample size is larger. Now, if you do make the same plot for a sample size of 2, which we really should not be doing, but it will show you how bad statistics is when you have only 2 replicates. Imagine these are 2 measurements, your 2 replicates. You can calculate standard deviation, you can calculate standard error for them, and you may be fooled to think that, you know, this standard error is really small, that's very good, our mean is very well constrained. But I told you a moment ago that for n of 2, interval, the 95% confidence interval, is 12 times the size of the standard error. So if you plot 95% confidence interval, which is a reasonable thing to do, it's enormous. It's much larger than the distance between these 2 points. So do not use 2 replicates in any of your experiments, because you will not have any statistical power. 3 replicates are kind of acceptable, but you have to remember that especially in complex biological experiments, things go wrong occasionally, and you might end up with 2 good replicates and 1 failed replicate, and 2 replicates again is not enough. So I always suggest having more, at least 4, maybe 5 or 6 replicates, just to be on the safe side. Have a look at this example. So imagine you do an experiment where you measure, you have a reporter that measures transcriptional activity of a gene. Let's say a fluorescent marker in your cell that tells you how a gene is expressed. And you did 8 biological replicates, 3 on one day and 5 on another day, because experiment is complicated and it takes a lot of time. Data are here, there are some numbers. And you can calculate 95% confidence interval on the first day and on the second day, and they're shown here. So this is the data from the first day, and this is data from the second day. You can immediately see that something is probably not quite right. And if you plot these confidence intervals, well, they do not even overlap. They are outside of each other. And if you do a statistical test, a t-test, it will tell you that probability of these things coming from the same distribution is very low. It's only about 3%. So you should probably reject this null hypothesis here, which means in practice, that means that there is a strong batch effect, that experiment done on one day looks different than experiment done on another day. Now, rather briefly, I will try to introduce you to the confidence interval of the median. And for this, we are not going to build a sampling distribution, because there is a simpler way. Imagine that you draw one random sample of n points from a population with unknown median, and I call the population median as theta. Now, the property of the median is very simple. the probability of having your data below median and above median is the same. It's 50-50, it's half. So you can use it for each point you draw from this population. You have a 50-50 chance of being either below or above median. Imagine we have, again, mice. We have 8 mice. We measure their body weight, and these are the numbers we obtained in grams. Let us assume for a second, we didn't know this, but let us assume that the true median in the population is 20 grams. So it's somewhere here in between 19.1 and 20.1. And the probability of each of this point being below and above median is 50%. We can compare it to a case when you toss a coin or 8 coins, and probability of having heads is 50% and probability of having tails is 50%. And now we can agree that this is what we represent, that if we have heads, our data point is below the median, and if we have tails, data point is above the median. And if you remember, this leads to a binomial distribution, and probability of this particular configuration, if you calculate it from the binomial distribution, is about 0.27. It's quite high. However, if the true median were at 15 grams here, then only one of our points, data points, measurements, would be below the median, and all others would be above the median. And probability of this particular configuration, if you calculate it from the binomial distribution, is much lower. It's about 3%. We can calculate, this is the binomial distribution, so we can calculate these probabilities for every possible location of the median. And location of the median is just between points 0 and 1, between points 1 and 2, and so on. The exact value of the median is not important. That's the property of the median, that values are not important, only ranks, how many points are below or above the given point. And now we would like to do something similar to what we did in the sampling distribution and reject 2.5% on each side. The problem is that this is a discrete distribution. We have only a few discrete numbers. If we consider that our confidence interval encompasses all data, so it starts below the first point and ends above the last point, then from the binomial distribution, you can calculate that probability of this is 99.2%. If you cut off 1 point here and 1 point there, then your probability drops to 93%, as you can see. So this is 0.004, this is 0.031, and we want 2.5%. So we want to be somewhere in between. And if you go to even more points cut off, you get 71%. So you can't calculate precise confidence interval on the median because there are only a few allowed confidence. You can calculate confidence interval of 99.2% or 93.0 for this particular data set, but of course it will change from data set to data set. So what you can do is an approximation. And there is something which is called Hodges-Lehmann estimator. And this approach is based on comparing all pairs of data and doing some interpolation. It's a bit complicated, but it tries to look at the entire distribution of your data and find the best approximation of the confidence of the median. How can you do this in R? You take your sample of your data points, exactly as in the previous slide, and you use function wilcox.test. This is for a Wilcoxon-signed rank test, or otherwise known as a Mann-Whitney test, which I will discuss with you later. So this is a statistical test, and if you ask it for confidence intervals, normally it won't give you this data, but if you put a parameter conf.int equals true, then it will give you lots of information, and among them there is also a 95% confidence interval for the median. So this is the way how you can practically find confidence interval of a median if you ever need to do so. And the last thing I want to mention today, just at the end, is well, a question of replicates. I already told you that you need your experiment to be done in biological replicates. Now, but the question is, how many replicates do you need? Okay, so replication is formally the repetition of an experiment under the same conditions. And typically it's the only way of estimating errors in your experiment. How many replicas do you need? Well, this involves statistical power, and I will devote entire lecture to statistical power later. But at the moment, I will show you just something very simple. Roughly speaking, there are two cases when you need to estimate number of replicas. You can get an estimate with a required precision, which I will explain you in a second, or you need to get enough sensitivity for a differential analysis, for example, for a statistical test. And that will be a topic of the lecture on statistical power. Now let's do something very simple. If you remember, we built a sampling distribution of the mean by repeating the same experiment with, let's say, 30 replicas multiple times. We find the mean, which is marked here by a vertical line. We collect all these means and build the sampling distribution of the mean. Standard deviation of this distribution is the standard deviation of the population divided by the square root of n. This represents uncertainty of the mean. Interval, which is about 2 times this sigma, corresponds to about 95% of the samples. If your sample size is large, let's say 30 or so, then it's about 2 sigma. So we can call this thing precision of the mean. Now, to obtain this precision, to get this precision, we need the sample size this. It is a simple, we simply calculate n from this formula, and n is 4 times sigma squared divided by epsilon squared. And to do this, you need an a priori knowledge of your population. You need to roughly know what the sigma, what the standard deviation is. And to do this, you can have, for example, a pilot experiment to do some rough estimates. And in our case of mice and body weight distribution, let's say that we know that the sigma is 5 grams. So if you know this somehow, this is only a very rough estimate, remember about it, but if you know this, then, for example, to obtain a required precision of plus minus 2 grams, so if you want the mean body weight of plus minus 2 grams with precision, you put these numbers here and you get 25. So you need a sample size of 25 to get this accuracy of the mean. And that is everything for today. Thank you very much.